Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 9 on partitioning a line segment. Now I'm going to want my calculator a little bit today and you will want one as well. Either a graphing calculator or even a scientific calculator will get the job done, but there are some calculations throughout the lesson today that it might be helpful to have this thing for. All right, that being said, let's get right into it and talk about what it means to partition a line segment. Now, in previous lessons, we learned about the side splitter theorem. One of the applications of this theorem allows us to partition or divide a line segment so that its parts are in a specific ratio. Now, before we get into that, because all of that work is going to be done in the coordinate plane, let's take a look at what it means to partition a line segment not in the coordinate plane. Exercise number 1. A segment is shown below whose length is 35. We would like to locate point P on segment AB such that it partitions segment AB into the ratio AP is to PB as 2 is to 3. Letter A. What must be the ratio of AP to AB? Explain. All right. Now I can't overestimate how important this first problem is, right? So let's begin by understanding this. AP to PB is equal to 2 to 3. That literally kind of means that if AP was a length of 2, PB would be a length of 3. Or if AP was a length of 4, PB would be a length of 6, etc. More importantly, it kind of means if I broke this segment into 5 equal parts, right? I don't know if that really are 5 equal parts, but if I broke this thing into 5 equal parts, right, then AP would be worth 2 of the parts and PB would be equal to 3 of the parts. All right, that's what this means, and it's really critical because then this is a piece of cake. If AP to PB is 2 to 3, then AP to AB, all right, would be 2 to 5, right? Because, if you will, AP plus PB has got to be equal to 5 parts. I'm not going to say that it's equal to 5 because it's not equal to 5, right? The whole segment's equal to 35, so AP plus PB can't be equal to 5, right? But it's equal to 5 parts, so 2 of those parts fit into AP, 5 of those parts fit into AB, so it's 2 to 5. Now, also a very important letter B. What does the ratio in A mean in terms of the lengths of AP and AB? Well, this really gets into what fractions are all about, right? If AP is worth 2 parts and the entire segment is worth 5 parts, then what this tells me is that AP is equal to 2/5 times AB, right? That is absolutely critical, right? Because what 2/5 of AB means is 2 1/5 of AB. So if I take AB, I break it into 5 equal parts, then AP represents how much is in 2 of those parts. Really, really important to this, right? So AP is 2/5 of the length of AB. All right, really, really, really important. Okay, and now, letter C, use B to find the length of AP using a single product, not using algebra. Okay, in other words, I don't want to do any AP divided by AB is equal to this divided by this. I just want to use this, right? The plain fact is AP must be 2/5 of the length of AB, so AP must be 2/5 times 35, and if you want, you could just do this kind of cross cancellation, and I will get that AP is 14, right? And again, just keep in mind, right, that if this was then 14, all of this would be 21, right? And then the ratio of AP to PB would be 14 to 21, which would then reduce down to 2/3 if I divided both of those by 7. All right? Now again, the really important piece here is if I have a segment that's broken into just two parts, okay, two parts, right? And I know their ratios, 2 to 3, then I can figure out how much either one of these is worth in terms of the whole by just saying, well, okay, AP must be 2 divided by 2 plus 3, or 2/5 of the whole. PB would have to be equal to 3/5 of the whole, right? And that is really important before we go on to partition a line segment. This is basic ratio work, basic fraction work, just understanding what it means for one thing, right, for a part to be a certain fraction of the whole. All right, let's keep going. So now let's partition, or the partitioning of directed line segments. We would like to be able to partition a line segment in the coordinate plane. Before doing so, we first must introduce a new idea, the directed line segment. So we already know about line segments. Now we're going to talk about what are called directed line segments. So let me bring this up there to the top. A directed line segment. A directed line segment is a typical segment that has a designated starting point and ending point. They are useful when thinking about motion along a straight line segment. All right, so let me just be very clear about this, right? Normally, when we have, like, let's say segment AB, right? Segment AB, segment BA, they're the same thing, right? But in exercise 2, we have a directed line segment that starts at A and ends at B, all right? In other words, we want to think about starting at A and moving along A to B, right? And that's different than starting at B and moving along it to A. Are the two segments the same? Yes, AB and BA are the same segment. But a directed segment literally says start at this point and end at that point. So that being said, let's take a look at exercise number 2. A directed line segment starts at A, 2, 13, and ends at B, 17, 3. Letter A. Calculate the change in x, delta x, and the change in y, delta y, for this directed line segment. Now, this is very important, right? We've done a lot of changes in x and changes in y. We do that for the slope formula, we do it for the distance formula, and generally speaking, it doesn't matter whether I do 2 minus 17 or 17 minus 2 for delta x. But in this case, we always have to do the final coordinates minus the initial coordinates. I'm going to say it again. The final coordinates minus the initial coordinates, because I want to know how much the x and y's change as I go from my starting point to my ending point. So in this case, right, delta x will be 17 minus 2, which is 15, and delta y will be 3 minus 13, which is negative 10. And again, this is critical. We have to do them in this order because what these two tell me is that when I go from A to B, my x-coordinate is increasing by 15 units and my y-coordinate is decreasing by 10 units. If the directed line segment was going from B to A, then my delta x would have been negative 15 and my delta y would have been positive 10, okay? And these numbers matter. Now, letter B, illustrate these changes on the graph by drawing in a right triangle with AB as its hypotenuse and vertical and horizontal legs. All right, so in other words, all I'm getting at is this idea, okay? If I'm at A and I move to B, what happens is that I'm increasing my x by 15 units and I'm decreasing my y by 10 units. So I have a positive 15 change here and a negative 10 change there. That's it, right? That's all I wanted you to illustrate. Positive 15 going this way and negative 10 going this way, and the arrows this time matter, right? That's why I didn't just draw sort of an arbitrary right triangle there. Now let's take a look at letter C. A point P lies on the directed line segment that partitions it into a ratio of 2 to 3, as in exercise 1. According to the side splitter theorem, how much of the change in x and the change in y should we add to the starting coordinates to find the coordinates of P? Use this to find the coordinates of P and plot it on segment AB. So here's what I'm talking about. Okay, and you might be like, what does this have to do with the side splitter theorem? Right, I took the picture that we had up here, okay, and I just sort of brought it down here. And what I did was I divided up segment AB into 5 equal parts, 1, 2, 3, 4, 5. And I put P after 2 of the parts, right? Because now AP has a quote length of 2 parts, and PB has a length of 3 parts. And again, you might say, well, what does this have to do with the side splitter theorem? Well, let's just say for right now, I took each one of these points along this line segment AB, and I drew in parallel lines to this vertical line. It would look something like that, right? And what I would see is that that would then divide this change in x into 5 equal parts, and I would want 2/5 of them, right? 2/5 of those parts give me how much change in x I'm going to get. And likewise, right, I could do the same thing, but draw in lines that are parallel to that horizontal line, and that will divide the y change into 5 equal parts, and I want 2 of those 5 equal parts. So the first piece is, how much of the change in x and change in y should we add to the starting point? 2/5 of it, right? I'm trying to write out the word fifth and I just can't. 2/5 of delta x and delta y, right? And again, the reason for that is that I really have 5 total parts. Now, it'd be easy as a student to go 2/3, right? Because you have 2 to 3. But that's really 2 and 3. It's really 2/5, all right? And the idea is I'm going to start at A, and I'm going to add 2/5 of that change in x to figure out my x coordinate of P. And then I'm going to start at A, and I'm going to add on 2/5 of the change in y to get the y coordinate of P. Now watch this. This is so cool, right? Our delta x, as we have on there, is 15. Our delta y is -10. So what's going to be the x of our partition point? Well, what were our starting coordinates? We went from, our starting coordinate were 2, 13. So we start at A at 2, 13. B is not that important, but I'm going to write it down anyway. Is at 17, 3. All right, so what's my partition point? Well, I'm going to start at my x coordinate, 2, and I'm going to add to it 2/5 of my change in x, right? So I'm going to take 2, my starting x value, right? I'm going to add to it 2/5 of the change in x. And of course, what is 2/5 of that? That's going to be 6. And I really want that to just be a normal plus. So I'm going to have an x coordinate of my partition point at 8. Likewise, my y partition point, that's going to take my initial y coordinate, and I'm going to add to it 2/5 of my change in y. Now my change in y is negative here, critical. So that's going to be -2 times 2. So that's going to be 13 plus -4. And that's going to be, whoops, not 11, that's going to be 9. And so my partition point should be at coordinates 8, 9. Now hopefully that point is even on there. So let's go up here. Let's go over to 8, 9, and there it is. And there is point P. And again, what's kind of cool is you should be able to actually sort of see it, right? I can actually kind of really divide this thing up. There are those 5 points, right? And they're each sort of spaced equivalently, right? Each one of these little distances is the same, all right? And all I had to do was add 2/5 of that x and 2/5 of that y to my starting point to figure out where my partition point is. Kind of neat, all right? And this takes a little bit of getting used to, but it's really, really simple. Once they give me that ratio, right, I can add the two numbers together to get my total, if you will. And then the fraction that I have to add on to my starting coordinate is simply that first number in the ratio, because that sort of is how far I have to go to get to the partition point. That divided by the total tells me how much of each of those two changes I need to add to the initial x and the initial y. So let's do some more of this. The partitioning formula. All right, now again, I'm going to make sense of this formula, but let's take a look at it. Partitioning a directed line segment in the coordinate plane. If a directed line segment that starts at x1, y1 and ends at x2, y2 is partitioned by a point P into a ratio of m to n, then the coordinates of P, x sub P, y sub P can be found by, let's take a look at this, kind of like pop out for a second, right? I'm going to always start with my coordinates of A. Okay, I'm not going to start with my ending coordinates. I'm going to start at my starting point and then move from there, right? M divided by m plus n is just the fraction of how much change I have before I get to the partition point. And I'm just going to do that fraction times my change in x, right? That'll get me how much total change in x I have that I have to add to my first x value. And then I'll do the same thing to the y value, all right? And that's all there really is to it. Right, I've got this partition line segment, some portion of it m before the first one, then n after it. So the whole fraction will be m divided by m plus n to get from here to here. And I just then add that fraction of the change in x, the total change in x, and that fraction of the total change in y. Okay? So let's play around with it a little bit. Exercise number 3. A directed line segment starts at A, 7, -3, and ends at B, -2, 9. Point P partitions the partition segment AB into a ratio of 1 to 2. Letter A, real simple, calculate delta x and delta y for this directed line segment. Okay, awesome. Well, why don't you go ahead and calculate those delta x and delta y, and then we'll talk about that and move on to part B. All right, now remember, we're going from point A to point B. And just by thinking about that, I should automatically know that my change in x is going to be negative and my change in y is going to be positive. But again, all I want to do is take my final coordinates and subtract off my initial coordinates. So my change in x is going to be -2 minus 7, which is -9. And my change in y is going to be 9 minus -3, which is positive 12, right? And again, makes sense, right? Because in order to go from A to B, I have to decrease my x and decrease my x a little bit more, decrease my x and then increase my y, right? So I'm making x smaller and then I'm making y larger. Now let's talk about what that fraction of change is. Let's take a look at letter B. What fraction of the changes in A should be added to the starting coordinates to find point P? Use this to find the coordinates of point P. Well, again, the idea is wherever P is, right, the distance from A to P compared to the distance from P to B would be 1 to 2. But that means, right, that wherever P is, it's 1/3 of the way along the segment, right? Not 1/2 of the way, then it would just be at the midpoint. It's 1/3 of the way, right? Because it's 1 part to 2 parts, so it must be 1 part to 3 parts overall. So if you will, the m over m plus n, right, is 1 over 1 plus 2, or 1/3 of the change. 1/3 of the change. Okay? And now it's easy. We can just come down here and we can say, all right, so I've got x sub p is, where do I start? I'm going to start at an x coordinate of 7. And I'm going to add on 1/3 of the change in x, which is -9. All right, that's going to be 7 plus -3. and that's going to be 4. All right. Why don't you go ahead and find the y-coordinate of the partition point? All right. Well, the y-coordinate of the partition point, let me bring this up a little bit. Once I write this down, right, I started a y-coordinate of -3, and I'm going to add to it 1/3 of my change in y, and that's going to be -3 plus 4, and that's going to be a coordinate point of 1. So point P should have coordinates of 4, 1. And letter C, easy enough, plot point P on AB. Let's take a look for 1 right there, right? And again, if you want to feel confident about your answer, you could do 2 things. 1, if that point actually lies on the line segment, that's a good sign. If it doesn't, you're definitely wrong, okay? So if you go through this calculation and you get a point hanging out here or down here, it's wrong. It's got to be on the line segment. But the other thing that you can kind of do at this point is you can sort of say, well, look, to go from A to wherever that point is, I'd have to go up 4 and to the left 3. If I then went up 4 and to the left 3, I'd get another point, and up 4 and to the left 3, I'd get my final point, right? And now you can really see that whole thing, right? Here, let me actually put point P on here, right? I can see that AP is sort of one section, and then P to B would be 2 of those sections, giving me that 1 to 2, right? And clearly AP is 1/3 of the length of AB, right? So you can really kind of verify that ratio if you've got something like this. All right, let's take a look at another one. Now, when we partition a line segment, we simply add the fraction of the total line segment that goes from the starting point to the partition point, right? That's all we do. And we shouldn't even need a graph grid to do it, although it is pretty handy and you can really see it. So let's take a look at exercise number 4. A directed line segment starts at M, 4, 12, and ends at N, 20, -12. Find the coordinates of point P such that MP to PN is 5 to 3. Okay, pause the video now and see if you can get through this. Okay, all your answers should come out nice and integers and things like that. We'll look at one where they don't come out as nice in just a moment, but see how much you understand about this process. Well, again, I love to first think about what is the total fraction, or what is the fraction of the total that I need to add on to my starting coordinates? Well, again, imagine that we take this line segment and we break it up so that the distance from M to P, the starting point to the partition point, compared to the distance from the partition point to the ending point is 5 to 3, right? 5 parts to 3 parts. But that means, right, that overall, my fraction that really matters here is 5/8, right? That's the fraction that really matters. I'm going to add 5/8 of the total segment onto my starting point in order to get to where my partition point is. Now let's figure out our delta x's and our delta y's. Right? My change in x is going to be 20 minus 4, which is 16. My change in y I have to be a little bit more careful about is going to be -12 minus 12, which isn't 0. It's -24. Okay, so I've increased my x-coordinate by 16 units and I've decreased my y-coordinate by 24 units. And I want to add 5/8 of both of those changes to my starting coordinates to get my partition coordinate. So my x-coordinate of partition will be my starting x plus 5/8 of my change in x. All right, 8 goes into 16 2 times, so I'll get 4 plus 10, and that will give me an x-coordinate of 14. The y-coordinate of my partition point will be my starting y point plus 5/8 of the change in y, which is -24. 8 goes into -24, -3 times. Okay, I can't lose that negative that's attached to the 3. So I'll get 12 plus -15, and that'll be -3. So P is at the coordinates 14, -3. That's it. That's the whole deal. All right. So one of the things that students like about these problems is that they are very mechanical. You could literally take the formula that I put in that box a few screens ago, and you could just plug numbers in. You could be like, m is 5, n is 3, 5 divided by m plus n is 5/8. Okay, now I've got x1 and y1 plus 5/8 times change in x plus 5/8 times change in y. But I hope you understand what is going on here. We're just starting at a particular location. We're saying, look, I know how much the x changed, I know how much the y changed to go from my starting point to my ending point. What fraction of that change do I have to add on to get to my partition point? And you can always figure that out by taking the first number in your ratio, which is really the distance to the partition point, divided by the sum of those two numbers, which is sort of the total distance. I have to put it in quotes because they aren't actually lengths, they're sort of our subdivisions, right? I divided the whole thing up into 8 parts. 5 of them came before the partition point, 3 of them came after the partition point. So 5/8 has to be added on to get to the partition point. All right. Now, certainly the coordinates of the partition point don't need to be integers. They oftentimes are on state exams, but I could easily conceive of a situation where they're kind of messy decimals, and that's where the calculator helps. So let's take a look at number 5. A directed segment starts at K, 3, 5, and ends at L, -8, 14. Which of the following are the coordinates of the point that partitions the directed line segment into a ratio of 3 to 2? Okay, well, I'd like you to pause the video and see if you can get through this. Again, you're going to probably want a calculator here because obviously whatever the answer is, it's got to be a little bit messy and involve decimals. All right, well, again, I start by first thinking about the fraction. Right, I've divided the segment really up into 5 equal parts, and the distance to the partition point represents 3 of those parts, so my fraction, right, my governing fraction, if you will, is equal to 3/5. All right, 3/5 of the change in x and the change in y have to be added on to my starting point to get to my partition point. Okay, so let's figure out our change in x and our change in y. Our change in x is -8 minus 3, or -11. And our change in y is going to be 14 minus 5, which is equal to 9. So I need to add 3/5 of my -11 and my 3/5 of my 9 onto my starting point, 3 and 5, to get my partition point. And this is where it's a little bit messy because neither -11 nor 9 are divisible by 5. So the x of my partition will be 3 plus 3/5 times -11, and we'll figure out what that is in a moment. And my y partition coordinate will be my starting y plus 3/5 times 9. All right, let's see what we have. And even on a simple calculator like this, I should be able to do it. 3 plus 3/5 times -11. Oh, really? Really? You're really going to do that? Okay, -18 divided by 5. Still no. Come on. -3.6. This is where that graphing calculator might work a little bit better than the scientific calculator. Now let's do 5 plus 3/5 times 9. I kind of understand why it's giving me the fraction. 52/5, so 52 divided by 5. I guess I could have just used the change it into a decimal button, wherever that is on here. And that's going to be 10.4. So I should have -3.6, 10.4, and that's choice 2. All right, that's it. And really, every one of these problems, one thing that's great about it, again, every one of these problems is essentially done the same way. All right? So partitioning a line segment is a classic problem that shows up on a lot of state exams, a lot of local exams, because it's literally in both the Common Core state standards and the next generation math learning standards, okay? Key in understanding partitioning a line segment is the idea of a directed line segment. Literally, we're starting at this point and we're ending at that point, right? Based on that, you then have to calculate specific change in x, specific change in y to get from one point to another point. You then are given a ratio of how much of that line segment occurs before the partition point, how much occurs after the partition point, and based on that you can figure out what fraction of those two changes must be added on to the starting point in order to get to the partition point. So play around with this on the homework. I hope it's a relatively easy topic for you because we won't see it that much more. We'll see it in the next lesson, but after that it pretty much fades away. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.